Good morning, friends. Today, our topic of discussion is the virtual screening, the aid methodologies, as well as the we'll start a brief discussion on combinatorial chemistry as well. So, we have already discussed different methods of virtual screening. That is the ligand-based virtual screening. In ligand-based virtual screening, we have already seen the methods based on how to if I don't know the target structure, if I only know the ligand structure, then using that ligand structure, how can I screen the use databases of compounds? For example, if I know the reference ligand of a particular genre, then I can use the similarity search using the similarity coefficient like Tanimoto coefficient or cosine coefficient or Euclidean distance or Jaccard coefficient, something like similarity search using chemoinformatics approach, using the binary digitization of various descriptors. Then we have discussed how to do the pharmacophore search. Okay, the manual or automatic pharmacophore generation, what is called the pharmacophore, what is meant by the pharmacophore generation, how the pharmacophores are fixed. Okay, then we have come to the machine learning approaches. In various machine learning approaches, we have discussed the first one, that is the weighted function method, and in discuss the second one, that is the recursive partitioning method in machine learning approaches. The other machine learning approaches like k nearest neighboring method of clustering or artificial intelligence networks, uh, this kind of machine learning approaches we'll discuss later. Okay, so what is recursive partitioning in virtual screening? Recursive partitioning means you have the combined library of compounds, you have the pool of library of compounds, and based on some logical functions, you are screening the compounds. That means you impart some logical functions on them, and if the compound satisfied yes, you segregate those one, and if satisfied no, you just segregate those one as well and just keep in a quarantine. In informatics approach, in drug discovery approach, the logical functions are based on the descriptors used in drug discovery approach. Not only descriptors, the different parameters like your substructural analysis or like your conformational analysis or like your topological geometries, then torsional angles, bond angles, then Lipinski rule of 5, the drug likeness all everywhere, which helps it to be acting as drug to bind with the receptor and to partition with the biological membrane. Those things you can have as logical functions here. Fine. So first, in this video, I have a brief demonstration of the whole step of the virtual screening by recursive partitioning. Okay. So now in recursive partitioning, you have this first one, we have this library of compounds. Fine, we have this library of compounds. Okay, these various colors including various libraries. So first logical function, say I have some reference compound, say I am I am doing the screening for the anti-diabetic or anti-inflammatory or whatever you like antidepressant or antipsychotic, whatever you choose. Okay, so first I have taken a reference ligand, say I'm doing the discovery of anti-inflammatory drugs, or say I'm discovering the antipsychotic drugs. Fine. So what I will do, first I will take a reference ligand of antipsychotic drugs. Say I have taken a tricyclic antidepressant. Say I have taken a tricyclic antidepressant like this. Okay. Say I am taking a tricyclic antidepressant like this 666 zonal. This is a phenothiazine ring up. Say the phenothiazine ring. Okay. This is the substitute one. Say I am taking this as a reference compound. So first I will see what microcosmic environment it is following based on this ligand structure description. What microcosmic environment, what the small parameters it is fixed inside the structure as a ligand. So say what is its pi value, the Hans constant, what is the ES value, the steric parameter, top steric parameter, what is the sigma value, that is the Hammett electronic constant, electronic distribution, what is its torsional angles, what are about its hydrogen bond donors and acceptors, what are its torsional angles, what are its topological distribution, everything. After I fix this, then I will use these descriptors to screen this library. For example, from first step, I use the logical function pi. I have seen its logical function say is more than 1.3. So I am setting the logical function. I say I have searched this string to say the logical, say the pi value is 1.5 or 1.6, something like that. Okay. So I am setting a logical function, say a small below than that. So pi is greater than 1.32. How many of these compounds are pi greater than 1.32? It has say 1.5. 5 or 5, 7, something like this. So how many of them is 1.32? So or it is 1.32. You can also set like 1. Say you can set this also like 1.5. It's up to you, or 1.6, up to you. Okay. How many of them is having this logical function greater than this? Say the if these compounds say yes and these compounds say no. Okay, these compounds say no and these compounds say yes. That means these compounds follow this first set of logical function. So I'm taking this one and I'm deleting this one. Now I am seeing that here the steric parameter maximum it goes 0.3. So I am setting the second logical function here. How many of these compounds have the steric parameter less than 0.32? The yes. Say this compound finds the logical function yes, and for this compound I find the logical function no. So I'm selecting these compounds which follows two logical function pi and yes. Then again I am attributing third logical function, that is sigma, electronic parameter. If you see say it is sigma, its maximum here is say 0.5, maximum 0.5. So I am maximum 0.5. So I am setting the logical function. How many of them is following sigma less than 0.48? So I'm going a little below than this. So this, the no ones I am deleting here. The yes ones I'm keeping here. Okay. Next time come to log p, the partition coefficient value. We know that you say I'm seeing the log p value is maximum like 2.8 or 2.9, something like that. So based on that, and also based on the Lipinski rule, you know the log p value cannot cross 5. It should be less than equal to 5. So based on these, and also from Lipinski rule of 5 knowledge, you attribute the log p value in between 0.1, 1.5 to 3. Why 1.5 here? Because if the log p value is very less, then there will be problem of permeation through blood-brain barrier or other biological membranes as well. So the minimum value of logical function I'm setting here, and the maximum value of logical function I'm setting here. So if the compounds passes through this logical function gateway, I will take this. So say out of these compounds, one compound is eliminated and rest 4 compounds passes this gateway. In the last one, I am setting some more logical functions as well. For example, I'm setting a torsional angle less than 2.5. I have seen from here. Then I'm setting the hydrogen bond acceptor should be greater than 1. By Lipinski rule of 5, I know that the hydrogen bond acceptor maximum can be 10, but I have seen in here sulfur and nitrogen, the two heteroatoms are hydrogen bond acceptors. So at least it should have one heteroatom here to be active. So I'm setting at least it should be greater than 1. It may be 2, 3, something like that, but at least may be greater than 1. And the last one, the topological descriptor, I have seen here by descriptor is that it is around, say, topological descriptor is around, say, 1.3 or something like that. So I'm setting the filter value 1.2. I'm setting the topological descriptor filter value 1.2. So those compounds which have the topological descriptor filter value 1.2, they will pass. So first another one I have also set a particular substructure, say this particular substructure, say I have these particular, say these two rings basically may be a very important substructure for exerting this biological activity. maybe because for all these compounds I have seen this substructure is present. Okay, actually for phenothiazide group of compounds, this particularly the whole substructure is present, but I'm keeping it simple for the timing. I'm taking, say, these two substructures are present, not on third one. In the third one, it may be vary a little bit. So, are the particular substructure present? That is also another logical filter I'm attributing. So, first I'm attributing a logical function, particular substructure is present. Those will pass, then it will pass to the second gateway, torsional angle less than 2.5. Those will pass to the third gateway, that is the hydrogen bond acceptor is greater than 1, that is the heteroatom greater than 1, and those will pass at fourth gateway, that is topological descriptor greater than 1.2. Okay, all this information, basic informations, I am coding from here, having the idea what a reference ligand is having. So after this four gateways, say I am having these two compounds. These two compounds are Wiener molecules. So these two compounds are likely to be bioactive. Okay. So say I am attributing some logical functions based on the reference ligand parameters, various descriptors and molecular parameters, and I am getting the ultimately the Wiener molecules. You may have more logical functions attributed here. That's not a problem. That depends on the researcher or the designer of the experiment. But this is the main essence how we do recursive partitioning in virtual screening. I've shown you a simpler way that can also be done in some like critical models like the substructural approach or the strings of substructures or the more topological different topological parameters like EXA, electrotopological state atom indices, other branching indices as well. Now, these logical parameters in recursive partitioning algorithm, if you fix the parameters in a loop, so it will run the loop and ultimately they will filter and get the final Wiener molecules like this. So this is the first one. We will discuss the recursive partitioning. Okay. So other machine learning approaches like artificial neuronal network or those kind of things we'll discuss later. Okay. The eigenvector analysis, all this we will discuss later. So next we will go to the structure-based virtual screening. How the structural-based virtual screening is done. Here we know the structure of the target protein. In the previous approaches, we didn't know the target structure, so we are doing the virtual screening based on the ligand, one reference ligand or more reference ligands, 5-10 reference ligands, something like that. But here we know the target structure, so our job is simpler because we know where the drug will bind to exert its activity. So we have the target binding portion. So based on that, we can easily screen out compounds. How it is done? It is done through docking. Okay. So what is docking? In docking, basically the artificially in software software or computer, the compounds are docked over the protein or target protein. Dock means hit over the target protein, and they are allowed to change its conformation. They are allowed to change their conformations to more favorable ones and subsequently bind with the protein. Okay. After the bind, some of them may get bind, some of them may not. And when they bind, they have different binding affinities. And we, from the drug receptor interaction theory, we know the more binding affinities they have, the more chance is that they will produce the more biological activity. Okay, so based on this theory, this structure-based virtual screening is done. This is one of the target protein. Okay, say this is the one of the target protein. So you are discussing about the antipsychotic drug. Antipsychotic drugs basically works on the dopamine receptor. So maybe the dopamine receptor, the dopamine binding protein is this. Okay. Now, or say if you are doing the anti-inflammatory drug screening, so maybe this is the COX or LOX receptor. Okay. Now you have this combination of library of drugs. There are various drugs. Now, first you download the structure of the protein from protein data bank. Say this is the protein structure. Okay, there are different loops, beta alpha helix, beta sheets, different barrels, and all these things. This is a loop. First, to analyze what are the binding pockets. First, to analyze what is binding pockets. The protein may have one or more than one binding pockets. If there is one binding pocket, you have to hit there, and if they have more than one binding pocket, then you have to find what is the main binding pocket and what is the allosteric binding pocket. Okay, say this is the main binding pocket. Okay, and this is the allosteric binding pocket. Say this is our allosteric. This is allosteric binding pocket. Okay, so this is our main binding pocket. Okay, so what we'll do, actually I will allow, because allosteric binding is also possible when a substrate approaches a protein, because sometimes the allosteric pocket changes conformation and the protein and the ligands or substrate attaching that may easily bind with them. So in this case, I will also allow the allosteric binding as well as the target binding. So in these two binding pockets, I will allow to hit all these ligands, all this library of ligands. So after it gets hit, now what will have, the ligands first, this is the binding pocket conformation, this is the binding pocket conformation. So those ligands which have the complementary configuration or conformation, three-dimensional or spatial conformation, uh, complementary to these binding pockets, only those ligands can fit and bind with these pockets, others are not. Fine. So based on this, say these ligands which have complementary structure to this pocket, they bind with this, and these ligands which have complementary structure to this binding pocket, they bind with this. But from this picture, you can clearly see there is more ligand binding, there is less ligand binding. Fine. So I'll choose this one because it is seem to be the major one to be exerting for biological activity. So I'll choose this one. Fine. Now, uh, after it, there are three things I need to say here. First of all, for this kind of docking, the main challenge is what conformation of ligand and what conformation of protein you should have, because inside protein, inside body, proteins and ligands both may change its conformation, because protein is not in a very rigid state in our body. Depending upon the temperature, pH, mobility of the blood, or mobility of the matrix it is within, they depend and change of microcosmic and macrocosmic environment surrounding it, is ionization, hydrophobic pockets, all of these, protein continuously changes its conformation. So it is under a flexible dynamics. Similarly, ligands also inside body, depending on the microcosmic and macrocosmic conformation, they are also in some kind of flexible dynamics. So they are depending on their flexibility. Four types of dockings are possible. First, this one, the flexible receptor and flexible ligand, when both are flexible. Second one, when the receptor is flexible but the ligand is rigid. Third one is when receptor is rigid and ligand is flexible. And the fourth one is receptor is rigid, ligand is rigid. First of all, both rigid we cannot take because that is deviating far away from our purpose, far away from the actual simulation inside body. Now, from the first three, which one to take? Now, protein conformational dynamics, to take protein conformational dynamics into account per second is a huge, humongous job, because protein is a very, very, very giant macromolecule, and to check all of its dynamics per bond, per torsion, per loops, per motifs is a very challenging job. Okay, so but ligand flexibility we can easily take in docking algorithm, because ligands are small molecules, so the number of bonds and atoms and torsions are limited, so we can allow all the bonds rotate freely so that all the torsional angles also can change. Okay, so the conformational dynamics we can take into ligand account. So we take the ligand flexible always. Always we take ligand flexible, but sometimes depending upon your software capacity, we take the flexible receptor or rigid receptor. In rigid receptor, what we do, we take a very reliable snapshot of the structure of the receptor. Say you download from PDB, most stable conformation from download from PDB, realistic conformation, and you use this conformation for the subsequent docking. Okay. Sometimes we also add some flexible residues to this. so that it becomes semi-flexible docking. We add some flexible residues, allow some residues to be flexible surrounding the binding site, so there is semi-flexible docking. Okay, semi-flexible receptor and ligand. And if you have if you can keep both flexible, then that is very good. If depending software capacity, you can do either this or this. So after you do the docking, these compounds are docked here, these compounds are bound here. So this is taken as the winners. Now the docking, after docking, the docking outputs are counted by Gibbs free energy, that is the free energy of binding. Okay, now when free energy of binding, this is a reaction, the receptor plus ligand gets that with receptor ligand complex by bond formation, by either polar or non-polar or hydrogen bond or van der Waals bond formation. Since there are bond formations, for their attachment to make a complex, we take it as a reaction. So when this is a reaction, we have to take the delta G, analyzed by its receptor kinetics. So receptor kinetics in thermodynamics, it says that when there is favorable change, the delta G comes negative, because the final complex energy is lower than the initial compound and proteins energy. Okay, but when they are zero, when delta G is zero, that means there is no energy change of the initial substrate and receptor and final complex, so energy change. So theoretically, the reaction is not possible. And if it is positive, that means the final complex will have more energy than the initial substrate and receptor. It is unfavorable. It can happen, but then for doing that, you have to apply external energy. That means you have to apply some more drugs or more substances which will produce energy inside body, which will produce irradiation or some kind of like phosphodiesterase bond breaking or some ATP production, some ATP to ADP production, so that the inorganic phosphorus come, or some kinds of energy will be there. So that is unfavorable. This is not the normal binding. So we always take the normal binding. So we'll always take the delta G negative. So first you have to take which ligands have delta G negative, and they set the value like 7.5. If this value increases like 7.5, 7.6, 7.8, then 8, 9, 10, that means what? The binding energy increase, that means it is more tightly bound with the receptor. So this, first we choose the minus values, then this value, the mod of this value, the magnitude of this value more increased to have the more increased binding. Say now I have cut off a filter minus 7.5 delta G. That means if it is having delta G less than that, that means minus 8.5. If it is minus, altogether it is going lesser. If this magnitude is getting higher, with this minus, the altogether it is getting lesser. So I am choosing delta G, I am putting minus a less than sign here. So if delta G goes minus to that, that means minus, if delta G goes lesser to this minus 7.5, that is minus 8, minus 9, minus 10, even minus 7.8, minus 7.9, I'll choose that is a good binding. Good binding with favorable binding. Good favorable binding. So I put how many winners of them having delta G less than minus 7.5. Okay, say minus 8 or minus 9, something like that, or at least minus 7.6, minus 1.8. So with this filter, say these three compounds have come out from these winners. That means these compounds are the most favorable conformation. These three compounds have favorable interaction with the receptor, has tightly bound with the receptor, and after docking, the conformations I obtain here, they are most favorable conformations having minimum potential energy. Because when docking is done, in docking you are allowing the ligand conformations to change. So the final conformation, that is binding with the receptor, the docking software will give you back most predictable 8 to 9 conformations. And analyzing these 8 to 9 conformations, you see which conformation has the lowest binding energy. That means that will be the most favorable conformation. And these favorable conformations usually have the minimum potential energy as well. Okay, so these three molecules having the most favorable conformation with minimum potential energy. These are my winners. Okay, these are my winners. Okay, now these winners, so this is the filter delta G. Yes, these molecules are following yes, and this molecule following no. So I'm choosing these three molecules as the winners from this library. That means these three molecules have the minimum energy conformation, have the most tightly binding energy with the receptor with favorable interaction with the receptor. So I can choose these three for my further drug molecule generation. Now, one more thing I am doing here, after I get through, what can I do? I can map the basic pharmacophore so that I can have the basic spatial electronic distribution of this molecule. That means if I map this basic 3D conformation of the molecule, basic spatial orientation of this molecule, whenever I will design drug, I will have this pharmacophore intact. Plus, when I will screen the further molecular database based on the theory of pharmacophore search, I can use this pharmacophore to search newer molecules from the database. So say from the three molecules I got here, that here is one electronic cloud, here is one, here is one, here is one, here is one, here is one. But the maximum distance, maximum Euclidean distance of the pharmacophore, if I map, is the basic geometry of the pharmacophore based on the maximum Euclidean distance is this. This is the x1 portion part, this is the x3 part, and this is the x2 part. x1, x2, this is coming as a triangle. If I count the Euclidean distance between the maximum distal points of this pharmacophore. So you have this point intact if you map, if you want to design further drugs in this journal. Okay, then these are the minor things. Just here we have also have the electronic binding, electronic distribution here. Then we have one electronic cloud here. Maybe it will produce some steric effect. Maybe this will also produce some steric effect. So this one we can change for our future drug designs. This is we can also manipulate to see that what changes are coming in our future ligands, what we are designing. Okay, but we have to keep this basic pharmacophore intact for the drug design or future screening of this database. So this is structure-based virtual screening. Fine. So up to this, we come to our end of the various methodologies that we usually encounter in the virtual screening. Various filtering techniques, various similarity search, quotient search, matrix search, pharmacophore search, and structure-based drug design, recursive partition-based drug design, structure-based virtual screening, recursive partition-based virtual screening, weighted function-based virtual screening. Okay. So this up to this, I'm concluding my lecture on virtual screening, and I'm going to the next topic, that is the combinatorial chemistry. Okay. To start with combinatorial chemistry, I'm going to this paper. In this paper, combinatorial chemistry is nicely summarized what is actually combinatorial chemistry. Okay. Well, actually, what is combinatorial chemistry? Combinatorial chemistry is basically nothing but synthesizing many compounds, a library of compounds at a single time. Synthesizing is of many set of compounds, various different compounds in a very short time and at the same time. So combinatorial chemistry definition is given like this. Combinatorial chemistry is defined. Combinatorial chemistry is defined as the systematic and repetitive covalent connection of asset of different building blocks of varying array of diverse molecular entities. That means systematic and repetitive covalent connection. That means it adds different building blocks or groups by covalent interaction of varying array of diverse molecular entities. That means the basic molecular entity is also varied, and on that the building blocks which are going to add, that is also varied. And they are getting it repeatedly, not for a single cycle. First cycle, then second cycle, then third cycle, then fourth cycle, then repeatedly. Okay. But this whole thing goes on a systematic way, as per your plan, which way you are going to add your substrate. Okay. This is the concept of basic chemical synthesis. Say I have this reagent, and this reagent. When I do a basic chemical synthesis, they are added together. Okay, that's all. This is our final product. But what in our combinatorial chemistry, what is done? The basic principle of this study is to prepare very large number of compounds and identify more components from these compounds. Okay? Researchers can synthesize many number of compounds short term by using simple methodology. Okay? Actually, what is the utility of this combinatorial chemistry? Say, when you are discovering drugs, we are doing drug design or molecular modeling, or you're doing de novo ligand design or structure based drug design, or say you are doing virtual screening, okay, to have some 5-6 winner compounds, or maybe you can have, or if you are do the virtual screening of like millions of compounds, maybe you are getting final 40, 50, 60, 100 of compounds. So based on this 40, 60, 100 compounds, how many are actually producing good biological activities? To measure that, you have to synthesize all these compounds. Okay. But how can you synthesize all these 40, 50, 60, 100 compounds in a shorter time? If you go for conventional synthesis, it may take you like years. And it's only if you take years only to synthesize compounds, how can you frame the biological activity of all of these? How can you test biological activity of this? So to solve that, scientists have found a beautiful ways to synthesize all these kind of compounds in a very short amount of time. And when you synthesize the compound in a short amount of time, you can screen the biological activity for all of them, and you can then discover good potent lead molecules having better biological activities. And then you can also subject these compounds for QSR, for 2D QSR, for 3D QSR, okay, for molecular modeling, and to design newer compounds in future. So the basic concept of combinatorial chemistry is this, that conventional reaction A plus B only give you AB, but in combinatorial chemistry A, there may be 1 minus n number of combinations of A, and in B there may be 1 minus n number of combinations of B. Okay, why 1 minus n? Because if there are n number of combinations, you start with 1. So if you start with 1, the remaining combinations are possible 1 minus n. Okay. Similarly, if you have n number of combinations of B and you start with any one combination, the remaining combinations are having like 1 minus n. So if you add these combinations, then the reagent, the product will form AB. These will also be having 1 minus n number of combinations. Okay. So this is the basic principle given in a small scale. Okay. Say this is A1, A2, and A3. This is the basic pharmacophores, and B1, B2, B3 are the substituents. So A1, B1 will be producing good biological activity, or A2, B2, or A3, B3. I do not know. Similarly, A2, B1, or A2, B2, or A3, B3. Which one will produce a better biological activity? Also, I do not know. Similarly, A3, B1, A3, B2, and A3, B3. Which one will produce the better biological activity? We do not know. So we have to synthesize all combinations. So in combinatorial chemistry, A1, B1, A1, B2, A1, B3, all three are produced. Okay. Then A2, B1, A2, B2, A3, A2, B1, A2, B2, and A3, B3, they are produced. And A3, B1, A3, B2, and A3, B3, also they are produced. Fine. So 9 different combinations, 9 different compounds are produced. Okay. So how this is produced? This is just go for this kind of linkages. How to design the combinatorial chemistry? First you have A, you are adding B, so you are getting AB. Then you are adding C, you are getting ABC. Then you are adding D, you are getting ABCD. So the chain is going up. The chain is going up. Okay. But say instead of now, if we have this step, now instead of adding D, if I add here D1, I will get ABCD D1. If I add D2, I will have ABCD D2. If I had D3, I will have ABCD D3, something like that. Okay. So this is the concept of designing of combinatorial chemistry. You can change the combinations here. You can change the varying building blocks here. Okay. This is one of this demonstration how to change the scaffold. The main scaffold means the main cavity or main three-dimensional space of a compound on which you can change various rings or substituents to have different combinations. Okay, so you see this is the main scaffold, and there are you have this kind of groups through which you can recombine this scaffold. So in one recombination, this square block is replaced with this triangular block. In another recombination, this circle is replacing this square block. Okay. In one combination, when this is triangle is there, keeping this triangle fixed, I am adding this one as the substituent here, NH substituent here. Then keeping the circle here, I am changing the NH substituent like this. So in all combinations, if you introspect, you'll see different combinations I can change, just keeping the scaffold intact. And like this way, I can generate the combinatorial library. I can generate the various potential compounds which may produce biological activities. Fine. Okay. So there are, so this is scaffold based technique, scaffold based library creations. Okay. Here is one example: amino acid and amino benzophenone libraries are produced using this scaffold based technique. Okay. Now, this is it is a scaffold based technique. You know the basic three-dimensional space of the molecule. Sometimes maybe that you do not know the basic three-dimensional space of the molecule, but you only know the backbone. You only know the backbone, basic what I will say, a template, the basic straight line which you know. From that also you can generate the combinatorial library. Example, nucleic acid and carbohydrate libraries. If you have the basic carbon chain as a backbone, you can have the carbon chain. If you have the carbon chain as a backbone, then you can generate these libraries. By varying the combination of aldehydes of ketone and hydroxyl group, you can generate various carbohydrate libraries. By varying purine or pyrimidine substituents, you can generate the nucleic acid libraries. So you can use the combinatorial library in various ways. Now, how to generate these libraries? There are several established techniques, like split and mix synthesis method is one of the technique. Like parallel synthesis method is another technique. Then in the parallel synthesis method, there is one very popular technique called T-back synthesis method. So we'll discuss these methods one by one. In today's lecture, I'll just discuss the first one, that is the split and mix method. What is split and mix method? This is the basic split and mix method workflow. Okay, this is the basic split and mix method workflow. How this goes on? You see, first you have the basic. For this kind of thing. You have the basic template ready. Say I have the basic carbon chain ready. Okay, I have the basic carbon chain ready. So these 3 3 3 9 9 9 9. So these are 27 resins. In 27 resins means the 27 carbon chains are there, and resins also act as backing membrane or the linker of combinatorial synthesis. Backing membrane means it is not directly participating in the reaction. It is acting as a vessel. It is acting as a rod on which you are doing the synthesis. It is acting as the bead on which you are doing the synthesis. After you finish the synthesis, you just cut this resin out and you have the compound. Okay. So first you have these resins, 27 resins, or 27, you may have 27 carbon chains as well, which is directly participating in the reaction. It depends on you, which you want to start with. They have the 27 resins in this picture. So first, in the first reaction, you are segregating, you are splitting. Splitting means segregating this 9 here, this 9 here, and this 9 here. So first, I am feeding this thing with A1 substituent. I am feeding this thing with A2 substituent. This here A1, here I feeding with A2, and here I am feeding with A3 substituent. So what will occur? The A1 substituent will attach here, A2 substituent will attach here, and A3 substituent will attach here. So first reaction is finished. Okay. So these 9 will have A1 substitutions, this 9 will have A2 substitution, this 9 will have A3 substitutions. This is first I splitted this, and then I did the reaction. After the reaction, I mix them. This is split and this is mix. I mix them. Okay. When I mix them, they are mixed like this in a vessel. So here I had all A1 to A3 substituent combinations. After that, I trickily again split them. Now, when I split, I will have each of the A substitution, each of the A substitution in each vessel. Each of the A substitutions in each vessel. That means there are three vessels. There I have three types of A combinations. So I am having three vessels. So in the first vessel, I have A1, A2, and A3. These three combinations. In the second vessel also, I have A1, A2, A3. These combinations. In the third vessel also, I have A1, A2, A3. These combinations. So these they are in three vessels. I have all these A1, A2, A3 combinations. Now in the first vessel, that means the second reaction, I am reacting with this B1, the second substituent or the second ring, that may be second substituent or that may be second ring. In the second ring B1, I am here adding second ring B2. I am adding second ring B3, second group B3. Okay. So if I have B1 here in the first vessel, so B1 will be attached on the first one also. So it will give you A1 B1 library. Then it will give you A2 B2, A2 B1 library, and in the third one it will give to A3 B1 library. Similarly, here in the first one, it will have giving A2 B2 library because B2 will be attached with all of this. Then in the second triplet, it will give A2 B2 library. In the third triplet, it will give A3 B2 library. Similarly, here in the first triplet, it will give A1 B3 library. In the second triplet, it will give A2 B3 library. And the third triplet, it will give in A3 B3 library. So now you see in the second reaction, I've already joined two groups, maybe two substituents or two rings or one substituent, one ring. Okay. So second reaction over after splitting. Then I will again mix. So when I will mix, I will having both A1 to 3 and B1 to 3 combinations here. A1 to 3, there's A1 to A3, and then B1 to B3. All combinations are present here. Okay. After that, again I split. Now, when I'll split, I'll tactfully split like this. In the third reaction, I will have first all A1, B1, A1, B1, then A1, B2, then A1, C2. Sorry, A1, B1, then A1, B2, then A1, B3. Okay. Then A2, B1, A2, B2, A2, B3. Then A3, B1, A3, B2, A3, B3. This kind of combination is possible. So I'm splitting like this. After that, I'm feeding with C1, C2, C3. Like here, I have fed with here B1, B2, B3. So when I'll feed with the C1, C2, C3, the chain will increase. That means C1 will be attached with all of these compounds, C2 will be attached with all of these compounds, C3 will be attached with all these compounds. Now, so I'll be having like chain like this. A1, it will be having A1 to 3 combination. Then B1, then B, I'll be having 1 to 3 combination, and then C, I'll be having 1 to 3 combination. For example, you may have like A1, B1, C1. Then you may be having like A1, B2, C1. Okay. Or maybe in the second vessel, you may have A2, A2, then B2, then C2. Or A2, then B1, then C2, something like this. In the third vessel, you may be having A3, then say B1, C3. Okay, or A3, B2, C3, like this. So after, so you see, just some mix and spool first reaction. Here is second reaction, third reaction. By 3 reactions, I can generate this huge kind of libraries. Okay, so here I am generating 27 compound library. Here I can generate maybe like hundreds of combinations from here. You can easily use the permutation combination formula to see what will be the actual library size in the third reaction if I use all these combinations. Okay, it may be like more than 100. It is more than 100. In the 3 reactions, I am hitting, creating various creating various compounds where the variations are more than 100. So this is the strength of combinatorial synthesis. You can generate the combinatorial library in a very quick clicks. It's like a click. It's going very quick clicks, very quick steps. Okay. So these are the advantages of the split and pool technique method of having choice for large libraries and less reaction vessels required. The disadvantage is less amount of synthesized compound available and 3/4 amount of resin bits necessary. It will require more resin bits, of course. But the compound library generation is not bad. It's also very good. Okay. So first we need to know what are the various techniques of what is combinatorial chemistry, how they are proceeded, what is the basic design of combinatorial synthesis, what is the difference between a combinatorial synthesis and a conventional synthesis, there is the power of library generation, how the scaffold is changed, how the backbone template is changed, and then we proceeded into a realistic method, that is split and pool technique, to see the power of library generation, how it is done. So that concludes my today's lecture. Thank you for attending my lecture. Okay, thank you.